Hello, and welcome to Architect of Sleep. Tonight, we are leaving the noisy world behind to travel to a vast and silent ocean of space, a cosmic desert 2 billion light-years wide. It is a place of profound quiet, where there is less than there should be, and where the universe itself seems to breathe a little faster. It is a place we call home. For now, just breathe, let your eyes grow heavy, and allow your mind to soften. Our journey begins now. In the quiet darkness of the cosmos, astronomers were counting lights, and they noticed something was missing. 3 scientists, Ryan Keenan, Amy Barger, and Lennox Cowie, were carefully mapping the universe in 2013. They were looking at tens of thousands of galaxies, tiny islands of light scattered across billions of light years. Their work was like making a census of the stars, counting how many galaxies exist in each region of space. But their numbers did not add up, a quiet puzzle hiding in the vastness. The missing light was a shadow cast all around us. Everywhere they looked near our own galaxy, there were fewer galaxies than there should be. This was not a small error, or a minor gap between stars. The deficit was huge. About 20% of the matter was simply not there. It was a profound emptiness, a hollow in the fabric of the universe, a silent whisper that our address in the cosmos was very, very strange. This vast emptiness was given a simple name, the KBC void. It was named for the 3 astronomers who first saw the emptiness, Keenan, Barger, and Cowie. But there is nothing simple about what it means for us. It suggests that our cosmic neighborhood is an exception to a very important rule. A rule that has guided our understanding of the universe for 100 years. A quiet exception to a grand cosmic law. The scale of this void is difficult to hold in the mind. It is a sphere of emptiness, with a radius of 1 billion light-years. That means it is 2 billion light-years from one end to the other. Our own Milky Way galaxy is only 100,000 light-years across. You could fit 20,000 Milky Way galaxies, end to end, just to cross this single void. It is a structure so vast, it dwarfs everything else we have ever seen. A true desert in the sky. According to our best theories, a void this large and this empty should be almost impossible. When scientists run computer simulations of how the universe evolved, they almost never produce a void like this one. To create a supervoid like the KBC, you need very rare conditions at the very beginning of time. The chances of it happening are less than 1 in 1,000. And yet, we are here, floating inside this statistical ghost. The scientists who found the void were very careful. They knew their discovery was controversial, so they checked their work again and again. They used data from multiple different galaxy surveys, looking at the sky from different angles, with different telescopes. They wanted to be sure they were not being fooled by an error or a trick of the light. But every time they checked, the result was the same, a quiet confirmation of a startling truth. The discovery immediately raised a deep and unsettling question. If we live in such an unusual place, does it affect everything we see when we point our telescopes at distant stars to see how fast space is expanding? Are we seeing the true speed or a distorted version? It is like trying to measure the speed of a river while sitting in a small whirlpool, a quiet doubt cast upon all our measurements. For years, there has been a quiet crisis in cosmology, a problem known as the Hubble tension. Scientists have measured how fast the universe is expanding using two different methods, and they get two different answers. This disagreement has been a persistent whisper of doubt, a small but significant crack in our picture of the cosmos, a puzzle waiting for a missing piece. The first method looks at the most ancient light, the afterglow from the Big Bang. This light is called the cosmic microwave background, or the CMB. It tells us about the universe when it was just a baby, and from it we can calculate how fast the universe should be expanding today. That number is about 67 kilometers per second for every megaparsec of distance. It is a prediction, a message from the past about the present. The second method looks at things much closer to us, like exploding stars called supernovae. This is a direct measurement of what is happening now, in our local part of the cosmos. But this method gives a different number, a faster one. It finds the universe is expanding at about 73 kilometers per second per megaparsec, a quiet contradiction between the past and the present. The KBC void offers a simple and elegant solution to this puzzle. If we live inside a huge region with less matter, then the gravity inside the void is weaker. The denser matter outside the void would pull on everything inside it. This outward pull would add extra speed to the galaxies moving away from us, making the local expansion appear faster than it really is, a cosmic illusion created by our empty home. This idea means we are not measuring the universe incorrectly. We are just measuring it from inside a hole. The extra speed from the void's gravitational pull could account for the entire difference between the two numbers. It would mean our local measurement is just a local anomaly. This resolves the Hubble tension without needing to invent new physics, a simple consequence of our unusual address. But this solution comes with its own deep unease. It means we must accept that our location is too special. We live in one of the rarest structures in the universe, a place that fundamentally biases our view of reality. This thought makes many scientists uncomfortable. It feels like a step backward, a return to an ancient idea that we are somehow at the center of something unusual, a quiet challenge to our sense of cosmic modesty. This idea challenges something called the Copernican principle. This is the idea that we are not special observers, that the Earth is not in a central, specially favored position. The KBC void suggests that while we are not at the center of the universe, we are in a very unusual part of it. This does not violate the principle, but it certainly strains it a quiet philosophical weight. Cosmic voids are not completely empty, which makes them even stranger. Their name suggests a perfect vacuum, but the truth is more subtle. Between the few lonely galaxies that drift through them, there is still a thin mist of dark matter and faint wisps of hydrogen gas, and everywhere there is dark energy, the mysterious force that pushes the universe apart, a ghostly presence in the silent dark. The main difference inside a void is density. The density of all this matter is incredibly low, far lower than the cosmic average. Because there is so little mass packed together, gravity barely functions here. Gravity is already the weakest force of nature, and in a void, it becomes almost irrelevant, a giant whose voice has faded to a whisper. In this realm of weak gravity, another force takes over. Dark energy becomes the dominant power in the void. In the denser parts of the universe, gravity fights against dark energy, pulling galaxies together. But inside a void, gravity is too weak to put up a fight. Dark energy wins easily, and its repulsive force takes complete control. A quiet king on a silent throne. As a result of dark energy's dominance, voids actually expand faster than the rest of the universe. They grow like bubbles in a loaf of bread, pushing their boundaries outward and compressing the filaments of galaxies around them. This creates a cycle that reinforces itself. As a void expands, it becomes even emptier, which in turn allows it to expand even faster, a process of runaway emptiness. Scientists have confirmed this faster expansion by watching how galaxies behave at the edges of voids. They have measured their speeds and found that they are rushing away from the void's center, faster than the overall cosmic expansion can explain. It is a strange and counterintuitive effect, where gravity causes things to move away from each other, a silent dance of cosmic repulsion. Light that travels through a void is also affected. As a photon of light passes through the vast emptiness, it experiences less gravitational influence. When astronomers look at the faint afterglow of the Big Bang, they see that the light that has passed through a large void appears slightly cooler. This is because the void has stretched a tiny bit, while the light was passing through, causing the photon to lose a small amount of energy, a ghostly fingerprint of emptiness on the oldest light in the universe. This effect is known as the integrated Sachs-Wolf effect. It is a very subtle change, but our instruments are now sensitive enough to see it. The cold spots in the cosmic microwave background perfectly align with the positions of known supervoids. It is a beautiful confirmation, a cross-check between the oldest light and the largest structures in the modern universe, a whisper across billions of years. The universe is not a smooth soup of galaxies. Instead, it is organized into a vast and beautiful structure, known as the cosmic web. On the largest scales, the universe looks like a sponge, or a piece of Swiss cheese. It is a network of dense walls and long thread-like filaments, surrounding enormous hollow pockets. This is the largest pattern in nature, a silent architecture that spans billions of light years. The densest parts of this web are the galaxy clusters. These are the great cities of the cosmos, where thousands of galaxies are packed relatively close together. They form at the intersections where multiple filaments meet. They are filled with hot gas and dominated by the gravity of dark matter, the bright, bustling hubs of the cosmic web. Stretching between these bright hubs are the filaments themselves. These are long chains of galaxies that trace paths through space, like glowing threads woven into a dark tapestry. Our own Milky Way galaxy lives in a small filament, on the outskirts of the Virgo cluster. We are in a quiet cosmic suburb, not the busy downtown. And in between all of this structure lie the voids. For a long time, astronomers did not know this structure existed. They saw a two-dimensional projection of galaxies. But in the 1970s and 80s, they began to measure the redshift of galaxies, a technique that reveals their distance. Suddenly, the three-dimensional picture snapped into focus, and the cosmic web was revealed in all its quiet grandeur. Redshift is like the Doppler effect for light. Just as the sound of a siren changes pitch as it moves past you, the light from a galaxy changes color as it moves away. The light waves get stretched out, shifting toward the red end of the spectrum. The amount of this shift tells us exactly how fast the galaxy is moving away from us, and therefore how far away it is, a cosmic echo that reveals depth. The origin of this magnificent web reaches back to the very beginning of time. In the first fraction of a second after the Big Bang, the universe was not perfectly smooth. There were tiny, random ripples in the density of space. Quantum fluctuations stretched to cosmic size. Some regions were a tiny bit denser than average, and others were a tiny bit less dense, a quantum blueprint for the future cosmos. Over hundreds of millions of years, gravity did its slow work. The regions that started out slightly denser pulled in more matter from their surroundings, becoming even denser. These structures lined up along the initial patterns, forming the filaments of the cosmic web. Meanwhile, the regions that started out slightly less dense lost matter to their neighbors, becoming the vast cosmic voids we see today, a silent testament to the power of patient gravity. Today, voids occupy roughly 90% of the volume of the universe. The filaments, walls, and clusters, where almost all the galaxies live, make up the remaining 10%. This incredible imbalance defines the character of our cosmos. We live in a universe of emptiness, punctuated by occasional islands of light. The KBC void is just one of these bubbles in the cosmic foam, but it happens to be our bubble. Our galaxy, the Milky Way, is not at the exact center of this great void, but we are deep within its influence. Measurements place us somewhere between 200 and 400 million light-years from the void's true center. This sounds like a huge distance, but the void itself is so vast, stretching 1 billion light-years from its center to its edge, that our position is still considered well inside the underdense region, floating in a cosmic low-density zone. Our larger cosmic family is also inside the void with us. The Milky Way belongs to the local group, a small collection of about 80 galaxies. The local group itself is part of an even grander structure, the Laniakea supercluster. This immense structure contains roughly 100,000 galaxies, yet even it is just a small piece of fluff inside the much larger KBC void, a quiet island of matter in a vast ocean of less. The name Laniakea is beautiful. It comes from the Hawaiian language and means immense heaven. It was named by astronomers at the University of Hawaii in honor of the Polynesian navigators who used the stars to cross the vast Pacific Ocean. Now we use the stars to map an even vaster ocean, the ocean of space, a name that connects the Earth and the sky. The void's influence on us is direct and measurable. Our galaxy is not sitting still. We are rushing through space, away from the center of a smaller, adjacent void called the local void. Our galaxy is moving at about 600,000 miles per hour. This is not part of the overall expansion of the universe. It is a peculiar velocity, a local motion caused by the gravitational imbalance of our strange neighborhood, a silent river carrying us through space. This constant outward flow changes how we see the universe. When we look out from inside the void, we are looking from a place that is moving faster than the average spot in the cosmos. All the galaxies inside the void with us are also being pulled outward. This creates a large-scale velocity field, a coherent pattern of motion that affects everything within the void's boundaries, a constant correction for our biased perspective. Our view of the cosmos is also shaped by our position. When we look out in any direction, we are looking through the void's emptiness until we see the wall of the void, the shell of denser matter that surrounds us. This shell appears as a concentration of galaxies at a distance of about 1 billion light-years. It is the shore of our cosmic ocean of emptiness. We are not sampling a random patch of the universe. We are sampling from inside one of its most extreme features, a quiet room with a very specific view. Because of this, the Hubble constant, the number that tells us how fast space is expanding, might be wrong for our local area. When we measure it using objects inside our void, we are measuring the expansion of space, plus the extra outward pull from the void itself. This inflates the number, making it seem higher than it is. It is like measuring the wind speed during a hurricane. Your local reading is accurate, but it does not represent the average wind speed across the entire planet. This local distortion could be the key to the Hubble tension. The measurement from the early universe, which gives a slower expansion rate, is a global measurement, reflecting the average properties of the entire cosmos. The measurement from nearby supernovae, which gives a faster rate, is a local measurement, taken from deep inside the void. The void's outward pull could perfectly explain why the local value is higher, a simple consequence of our unusual cosmic address. If this is true, it means the universe's true expansion rate is the slower one. The value of 67, not 73. This has profound implications. A slower expansion means it took longer for the universe to reach its current size. This would confirm the age of the universe to be about 13.8 billion years old, which agrees with the ages of the oldest stars we see. It would make our cosmic story consistent again, a quiet resolution to a nagging paradox. This solution, however, still leaves a philosophical puzzle. It requires us to abandon the cosmological principle, the idea that the universe is the same everywhere, on large enough scales. It means we must accept that we live in a special place, a place that is statistically rare, and that our observations are fundamentally biased by this location, a quiet challenge to our sense of cosmic modesty. Our best description of the universe is called the Standard Model of Cosmology. This model, known as Lambda CDM, has been incredibly successful. It explains the afterglow of the Big Bang, the formation of galaxies, and the abundance of different elements. It is the bedrock of modern cosmology, but the Hubble tension, if not explained by the void, suggests that this model is incomplete, a quiet flaw in our understanding. The name Lambda CDM comes from its two main ingredients. Lambda represents dark energy, the force driving cosmic acceleration. CDM stands for cold dark matter, the invisible substance that provides the gravitational scaffolding for galaxies. This model has been our guide for decades, but the Hubble tension might be pointing to a crack in its foundation, a quiet hint that something is missing. A faster expansion rate would make the universe younger. If the local, faster measurement were true for the whole cosmos, the universe would be only about 12.7 billion years old. This creates an immediate problem, as there are stars in our own galaxy that appear to be 13 billion years old. It is a logical impossibility for stars to be older than the universe they live in, a silent contradiction written in the light of old stars. The expansion rate is also deeply connected to dark energy. This mysterious force is what drives the accelerating expansion of the universe. Our understanding of its properties is based on the expansion rate we measure. If that rate is different from what we thought, then our theories about dark energy might be wrong too. Perhaps dark energy is not a constant force, but something that changes over time, a quiet hint from the expanding darkness. Scientists have explored other ways to solve the Hubble tension. Perhaps there are subtle errors in the measurements. Maybe the exploding stars we use as cosmic mile markers are not as standard as we think. Researchers have spent years searching for such errors, and have so far found none that are large enough to explain the discrepancy. The measurement seems solid, a persistent and quiet puzzle. Another radical idea is to change our theory of gravity. Einstein's theory of general relativity has been perfect for over a century, but maybe it breaks down on the very largest cosmic scales. This is a dramatic step, like rewriting the rules of the game. However, the KBC void hypothesis offers a much simpler path. It does not require new physics, just a new perspective on our place in the cosmos. Inside a cosmic void, gravity does something strange. It effectively pushes things outward. This is not because the force of gravity reverses. Gravity always pulls, but in an underdense region, all the mass is on the outside. Imagine standing in a large shallow bowl. The gravity from the heavy rim would pull you away from the center of the bowl. This is what happens to galaxies inside a void, a silent outward tug. This outward pull creates a systematic flow, a river of galaxies streaming away from the void's heart. This motion is not random. It is a coherent outflow that affects everything inside the void. When we measure the speeds of galaxies near us, we are measuring this outflow on top of the normal cosmic expansion. This is why our local measurement of the Hubble constant is higher, a silent current in the river of time. Our own galaxy is caught in this current. The Milky Way is moving at a staggering speed, about 600,000 miles per hour. This is our peculiar velocity, our motion relative to the overall cosmic flow. This speed is the result of all the gravitational tugs in our local environment. We are being pulled toward the massive Virgo cluster and pushed away from the local void, a silent passenger on a cosmic journey. This high speed is itself strong evidence for the void. In a normal average region of the universe, peculiar velocities are much smaller. Galaxies move around a bit, but there are no large, coherent flows. The fact that we are moving so fast, and that entire regions of space around us are moving together, points to a very large-scale gravitational imbalance. Our speed is a whisper from the emptiness, telling us that our neighborhood is not normal. This leads back to the cosmological principle. the idea that no place is special, the KBC void and the rapid flows it generates seem to be a clear violation of this principle. It suggests that the universe is not as smooth and uniform as we have long assumed. Science has a long history of showing us that we are not in a special place. The void seems to run counter to this trend, a quiet anomaly in the grand design. The seeds of these great voids were planted in the first moments of creation. During a period of incredible expansion called inflation, just a fraction of a second after the Big Bang, the universe was a sea of quantum energy. Tiny, random fluctuations, ripples in this primordial sea, were stretched to enormous sizes, creating a quantum blueprint for the future cosmos. These tiny initial differences were all that gravity needed. Over the next 13.8 billion years, gravity worked on this blueprint. The slightly denser regions had a slight advantage. They pulled in more matter, growing denser still, and eventually collapsing to form the stars, galaxies, and clusters that make up the cosmic web, a slow and patient construction. At the same time, the regions that started out slightly less dense lost the battle. Matter flowed away from them, drawn toward their denser neighbors. These regions became progressively emptier, expanding and merging with other empty regions to become the vast cosmic voids, the silent echoes of the universe's initial quantum state. The cosmic microwave background, the faint light from the early universe, is a direct picture of these initial ripples. When we look at its temperature, we see a map of the hot and cold spots that correspond to the denser and less dense regions of the infant cosmos. This map is the seed of everything we see today, a stunning confirmation of our cosmic story. But there is a catch. While computer simulations create a cosmic web filled with voids, they very rarely create a void as large and as empty as the KBC void. To do so requires a very specific and very unlikely initial ripple. This is the heart of the statistical problem. The existence of our void suggests that either we are the winners of a cosmic lottery, or our simulations are missing something fundamental, a quiet flaw in our understanding. This has led some scientists to wonder if our theories need to be adjusted. Perhaps the initial quantum fluctuations were not completely random, but had some hidden structure that favored the creation of large voids. Or perhaps gravity itself works differently on these immense scales. These are radical ideas, but the existence of the KBC void forces us to consider them, a silent invitation to think differently. Because voids are so empty, they are the best places in the universe to study dark energy. In the dense filaments of the cosmic web, gravity is strong, and its effects are tangled up with the effects of dark energy. But in a void, gravity is so weak that dark party energy is the only force that matters. This makes voids a clean natural laboratory for probing the nature of this mysterious cosmic force. By studying how fast voids expand, scientists can measure the strength of dark energy with great precision. If dark energy is a constant property of space, then all voids should expand in a predictable way. But if dark energy changes over time, then the expansion of voids would be different. Voids are like cosmic barometers, measuring the pressure of dark energy throughout the universe. The shape of voids also holds clues. If dark energy pushes equally in all directions, then voids should remain roughly spherical as they expand. But if dark energy has some hidden directionality, then voids might become stretched or distorted. By carefully mapping the three-dimensional shapes of thousands of voids, astronomers can test whether dark energy is truly uniform, a silent geometry that reveals the laws of physics. The galaxies that manage to live inside voids are a special breed. They grow up in profound isolation, unlike the crowded galaxies in clusters, which are constantly interacting and colliding. This lonely upbringing shapes everything about them. Void galaxies tend to be smaller, fainter, and more pristine than their city-dwelling cousins, the quiet country folk of the cosmos. Because they rarely collide with other galaxies, void galaxies often retain their beautiful spiral structures. They are not twisted and disrupted by gravitational encounters. They also hold on to their reserves of gas, the raw fuel for making new stars. They are like quiet reservoirs of potential, preserving the conditions of the early universe in their undisturbed state, a silent history of gentle creation. These isolated galaxies are also often bluer in color. In astronomy, blue means young, hot stars, because void galaxies have not had their gas stripped away by collisions. They can keep forming new stars at a slow, steady rate. This continuous, gentle star formation gives them a bluish tint, a sign of quiet, ongoing life. The paradox of our local supercluster, Laniakea, is that this massive structure of 100,000 galaxies exists entirely inside the KBC void. How can a supercluster be part of an empty region? The answer is a matter of scale. The void is underdense on average, over its immense 2 billion light-year span. But it is not perfectly empty. It contains smaller filaments and structures within it. Laniakea is one of these, a vast island in an even vaster ocean of emptiness. To measure these vast structures, astronomers use a clever technique called baryon acoustic oscillations. These are the frozen echoes of sound waves that traveled through the hot, dense plasma of the early universe. These sound waves left a faint imprint on the distribution of matter, creating a preferred distance between galaxies, a standard ruler woven into the fabric of the cosmos, a silent yardstick for measuring the universe. These ancient sound waves created a shell of matter at a specific distance from any starting point. This distance is about 500 million light-years. It means that galaxies are slightly more likely to be found at this distance from each other. This pattern is the standard ruler, a faint echo of a sound that once filled the cosmos. By using this cosmic ruler, astronomers can map the universe in 3 dimensions with incredible accuracy. And these maps clearly show the KBC void. When they measure the galaxy distribution around us, they see a clear deficit, a region where the galaxies are spread farther apart than the standard ruler would predict. The ancient echoes of sound waves are now helping us to map the silent emptiness of our cosmic home. The oldest light in the universe, the cosmic microwave background, also carries the void's fingerprint. As this ancient light travels through a void, the expanding emptiness saps a tiny amount of its energy, making the light appear slightly cooler. Astronomers have looked for this effect and found it. when they point their telescopes at known voids, they see a corresponding cold spot in the microwave sky, a ghostly shadow cast by the great voids across 13.8 billion years of cosmic history. In another part of the sky, there is an even larger void, called the Eridanus supervoid. This void is associated with a feature known as the CMB cold spot, a region of the microwave sky that is unusually cold. This supervoid is about 1.8 billion light-years across, and it is one of the largest structures ever discovered. Its existence, along with the KBC void, suggests that these giant empty regions might be more common than our standard theories predict. A quiet hint that the universe is lumpier than we thought. The idea that we live inside a Hubble bubble has emerged to describe our situation. Inside this bubble, which corresponds to the KBC void, our measurements of the Hubble constant are inflated. Outside the bubble, the universe expands at the slower, true rate. This predicts that as we look farther and farther away, the measured expansion rate should decrease. Recent observations are beginning to hint that this is exactly what is happening. A quiet confirmation that we are seeing the edge of our own bubble. The future of these voids is one of inexorable growth. As dark energy continues to push the universe apart, the voids will expand faster and faster. They will eat away at the filaments of the cosmic web, pushing galaxy clusters farther and farther apart, until they are completely isolated. The universe's ultimate fate is to become a cold, dark, and mostly empty place, a silent, lonely end to the cosmic story. In this distant future, any civilization that arises within a galaxy will be cosmically isolated. They will look out into a sky that is almost completely black. The other galaxies will have receded beyond the horizon. The afterglow of the Big Bang will have faded into undetectability. They may never know that there was a Big Bang, or that the universe is expanding, a quiet prison of emptiness. We live in a special time, a cosmic dawn, where the sky is still full of light, and the story of the universe can still be read in the stars. We can see the distant galaxies, we can measure the cosmic expansion, and we can detect the faint echo of creation. We are lucky enough to live in a time and a place where the universe has not yet hidden its secrets from us, a brief, shining moment of clarity. The void acts as a kind of cosmic filter. It prevents the largest structures from forming within it. In the dense parts of the universe, gravity can build massive galaxy clusters, enormous cities of light, but in the void, the density is too low. Gravity is too weak to gather that much matter in one place. The void remains a place of small towns and lonely highways, a quiet, underdeveloped landscape. This filtering effect shapes the galaxies themselves because they do not merge with other galaxies as often. Void galaxies are less likely to become giant elliptical galaxies, which are the product of many cosmic collisions. Instead, they tend to remain as elegant spiral galaxies, their delicate arms preserved in the quiet solitude of the void, a gallery of pristine cosmic art. The gas between galaxies, the intergalactic medium, is also different in voids. In dense clusters, this gas is superheated to millions of degrees by collisions and cosmic shocks. But in voids, the gas remains cooler and less disturbed. It is a more pristine sample of the material left over from the Big Bang, a quiet reservoir of ancient hydrogen. This process is self-reinforcing because voids cannot form large structures. They remain quiet and underdeveloped. This means they do not have the violent events, like massive cluster mergers, that heat up the gas and drive rapid evolution. The quiet places stay quiet, and the busy places get busier. The universe becomes a place of ever greater contrasts, a silent sorting of cosmic destinies. Massive projects like the Sloan Digital Sky Survey have been crucial to this work. These surveys are like cosmic cartographers, painstakingly measuring the positions and distances of millions of galaxies. It is through these incredible maps that the true three-dimensional structure of the cosmic web and the vastness of the voids has been revealed to us, a picture drawn with points of light. Our motion through space is called a peculiar velocity. This is our speed relative to the smooth, overall expansion of the universe. It is caused by the gravitational pull of nearby structures, like a small boat being pulled by local currents in a great wide river. Our high peculiar velocity is a key clue that we are in a region with strong local currents, a region like the edge of a great void. All the matter in our supercluster, Laniakea, is flowing toward a single point, a deep gravitational well known as the Great Attractor. This is a huge concentration of mass, millions of billions of times the mass of our Sun, that lies about 150 million light-years away. We cannot see it directly, because it is hidden behind the plane of our own Milky Way galaxy, a hidden giant pulling us forward. But even the Great Attractor is just part of a larger flow. Our entire Laniakea supercluster is being pulled toward an even more massive structure, the Shapley supercluster. This is the largest concentration of galaxies in our local universe, a cosmic heavyweight whose gravity is felt for hundreds of millions of light-years. It is a reminder that there is always a larger scale, a bigger structure just beyond our view, a quiet hierarchy of cosmic giants. This creates a beautiful and complex dance of cosmic flows. Galaxies flow toward clusters, clusters flow toward superclusters, and superclusters flow towards the greatest attractors. All of this motion is happening on top of the overall expansion of the universe. It is a picture of incredible dynamism, a silent, swirling ballet on the grandest of scales. There are other ways to check the age of the universe, besides the expansion rate. One method is to look at the coolest, faintest white dwarf stars. These are the dead cores of Sun-like stars, and they cool down at a very predictable rate. The oldest ones we can find have been cooling for about 12 to 13 billion years. This provides an independent clock that agrees with the older age of the universe, a silent ticking in the cosmic graveyard. The very oldest stars in our galaxy tell a similar story. These stars are found in the faint halo that surrounds the Milky Way. They are extremely metal-poor, which means they formed from the pristine gas of the early universe before many generations of stars had a chance to create heavier elements. They are like fossils from the dawn of our galaxy, living relics of a bygone era. We can measure the age of these ancient stars with great precision. We do this by looking at star clusters, where all the stars were born at the same time. By seeing which stars have finished their lives and which are still burning, we can determine the age of the cluster. This method, called the main sequence turn-off, consistently gives ages of around 13 billion years for the oldest clusters, a quiet consensus written in starlight. A space telescope called Gaia has made these measurements even more precise. Gaia has measured the exact distances to millions of stars, which is the most important piece of information for calculating their true brightness and age. This new data has confirmed the ancient ages of these star clusters, strengthening the conflict with a younger universe, a quiet verdict from a precise cosmic surveyor. The coherent motion of large groups of galaxies is called bulk flow, and this is another area where our local universe is strange. Observations show that huge regions of space, hundreds of millions of light-years across, are all moving together in the same direction, at speeds much faster than standard theories would predict. This is another piece of the puzzle, pointing to a large-scale gravitational imbalance, the signature of a giant void. A huge collaborative effort called the Cosmic Flows Project has been dedicated to mapping these motions. By compiling the peculiar velocities of tens of thousands of galaxies, they have created a three-dimensional map of how matter is moving in our cosmic neighborhood. These maps show a clear outflow from our region, consistent with the pull from the great voids and attractors that surround us, a detailed portrait of our silent cosmic river. Some have wondered if gravity itself is different. A theory called modified Newtonian dynamics, or MOND, suggests that gravity is stronger on very large scales than Einstein's theory predicts. This theory was invented to explain why galaxies spin so fast without needing to invoke invisible dark matter. It is a radical departure from mainstream physics, a quiet whisper of a different law. In a universe governed by MOND, structures like galaxy clusters and voids would form more easily. The enhanced gravity would create deeper voids and denser filaments. Computer simulations using MOND can actually produce voids as large as the KBC void, without it being a statistical fluke. For supporters of this theory, our void is not an anomaly. It is a prediction, a quiet confirmation of their ideas. To measure cosmic distances, astronomers rely on standard candles. These are objects that have a known, predictable brightness, like a light bulb of a specific wattage. The most famous are Type Ia supernovae, exploding stars that all reach the same peak brightness. By measuring how faint they appear, we can calculate how far away they are, a simple and powerful tool for mapping the cosmos. But there is another tool, the standard ruler. This is an object or a pattern with a known physical size. The baryon acoustic oscillations are the universe's primary standard ruler. It is a fixed length, woven into the cosmic web itself. By measuring how large this ruler appears at different distances, we can map the geometry of space and the history of expansion, a cosmic measuring tape left over from the Big Bang. These two methods, standard candles and standard rulers, are wonderfully different. Candles rely on the physics of stars, while rulers rely on the physics of the early universe plasma. The fact that they both contribute to the Hubble tension, but can also be used to confirm the void's existence, shows the richness and complexity of modern cosmology. A beautiful interplay of different cosmic clues. The space between galaxies is almost perfectly empty, but not quite. The density of matter in a void is so low that if you had a box the size of the Earth, you might find only a single atom inside it. It is a level of emptiness that is difficult to comprehend, a silence that is almost absolute, a profound and peaceful nothingness. The faint wisps of hydrogen gas that drift through the voids are incredibly thin. They are the leftover scraps from the feast of galaxy formation. Gas that was never pulled into a gravitational fold. It is millions of times less dense than the air you are breathing. A ghostly mist that traces the faintest outlines of the cosmic web. A silent breath in the cosmic dark. Even the dark matter in voids is spread thin. While dark matter makes up the bulk of all matter, in a void, its density is only about 15% of the cosmic average. It still forms vast, invisible halos, but they are far more diffuse than the halos around galaxies in dense filaments. It is a gentle, invisible scaffolding that holds the void's sparse contents together. A silent, unseen structure. The slow evolution of void galaxies is a study in peace. They are spared the violent collisions and mergers that shape galaxies in crowded environments. They can live for billions of years, gently turning, their spiral arms slowly winding, their star formation proceeding at a slow and steady pace. They are a picture of cosmic tranquility, a silent meditation on slow time. The lack of mergers means that void galaxies have a different destiny. In dense clusters, mergers create giant, bloated elliptical galaxies with no new stars. But void galaxies are likely to remain spirals for their entire life. They will slowly fade as their gas is used up, but they will not be torn apart and reformed by cosmic violence. A quiet life from beginning to end. The chemical composition of void galaxies is also unique because they form stars more slowly. They are less enriched with heavy elements. These elements, which astronomers call metals, are created inside stars and released when they die. Void galaxies have a lower metallicity, making them more similar to the galaxies of the early universe. They are chemical time capsules, preserving a piece of the cosmic past. This raises a curious question about life. Could life spread between stars, or even galaxies? A process called panspermia. In dense clusters, this might be possible, as stars are much closer together. But in a void, the distances are immense. It is almost certain that if life were to arise in a void galaxy, it would be an isolated event, a lonely spark of consciousness in a vast and silent ocean. So are voids good or bad for life? On one hand, they are quiet and stable, free from the sterilizing radiation of nearby supernova or active galaxies. On the other hand, their lower metallicity might mean fewer rocky planets and fewer of the chemical building blocks of life. It is a cosmic trade-off between safety and resources, a quiet question with no answer. Because of dark energy, our cosmic horizon is shrinking. The boundary of the observable universe is not fixed. As space expands faster and faster, light from the most distant galaxies will no longer be able to reach us. They will be carried away by the expansion of space, faster than the speed of light. Their light will fade, and they will disappear from our sky forever. A slow and silent farewell. On the longest of timescales, the universe's fate is even stranger. After trillions and trillions of years, even the black holes that remain will evaporate. They will slowly radiate their mass away as heat, a process called Hawking radiation, until nothing is left. The universe will become a cold, dark, and infinitely expanding sea of low-energy particles, the final, quiet state of everything. We exist in a fleeting moment of cosmic richness, a time when the universe is filled with structure, with light, and with information. We are close enough to the beginning to see its faint glow, and far enough along for complex structures like galaxies, planets, and ourselves to have formed. It is a privileged moment, a brief window of cosmic clarity, a quiet gift of time. There are even voids within voids, a strange cosmic hierarchy. Just as our Laniakea supercluster is a structure inside the KBC void, there are smaller, emptier regions inside Laniakea itself. The universe is not just a simple sponge. It has a complex, fractal-like structure with emptiness on many different scales, a quiet, nested reality. Voids can also affect light in another strange way, through gravitational lensing. Massive objects bend light, acting like a lens, but a void, because it has less mass, does the opposite. It delenses light, causing distant objects seen through it to appear slightly smaller and farther away. It is a subtle distortion, a quiet trick of the light caused by emptiness. The James Webb Space Telescope is a powerful new tool to study these ideas. By peering deeper into space than ever before, it can see the very first galaxies that formed. It will measure their distribution and properties. This will give us a much clearer picture of the early cosmic web and test whether our simulations of how voids form are correct. A new eye on the ancient universe. There are other strange patterns in the sky, besides the cold spots. Some studies have found a strange alignment in the cosmic microwave background, a pattern called the axis of evil. This pattern seems to align with the plane of our own solar system, which is very strange and unexpected. It is another hint that there might be something unusual about our place in the cosmos, another quiet cosmic mystery. The first stars in the universe lit up the darkness in an era called Ryanization. This is when their powerful light stripped electrons from the neutral hydrogen gas that filled the cosmos. This process happened first in the dense filaments, and last in the voids. The voids were the final pockets of darkness to be illuminated, the last quiet corners of the young universe. Even the most mysterious particles, neutrinos, might be connected to voids. Neutrinos are incredibly light, and they travel at nearly the speed of light. Because they are so fast, gravity has a hard time capturing them. Some theories suggest that neutrinos might accumulate in voids, where gravity is weakest. Voids could be vast, invisible reservoirs of these ghostly particles, a silent gathering of cosmic phantoms. We have traveled through an immense emptiness, a quiet place that shapes our view of everything. It reminds us that even in the vast dark, there is a strange and gentle order, a silent architecture of space. Our journey through this cosmic desert reveals not an absence, but a different kind of presence, a quiet that holds the secrets of the universe. The void is not a flaw in the cosmos, but a feature. It is a necessary part of the great cosmic web, the yin to the yang of the bright filaments and clusters. Without the voids, the universe would not have the grand structure we see today. It is the emptiness that gives the fullness its shape, a silent partnership of something and nothing. And so we float in our quiet corner of this immense heaven, carried on a silent river of space. Our view of the universe is unique, shaped by the vast emptiness that surrounds us. It is a humbling thought, but also a beautiful one, a reminder that our perspective is just one of many, in a cosmos far grander than we can ever fully know. If you enjoyed this quiet journey, I am glad you found your way here. It helps others find this peaceful corner too, one sleepy soul at a time. And now, just breathe. Let your eyes close, and let the quiet void lull your thoughts to sleep. Good night.